If you started this clock 13.8 billion years ago, at the exact moment of the Big Bang, it would not have lost a second by today. Global infrastructure, including GPS and high-frequency financial networks, relies on a single global standard of time, the microwave Cesium clock. Microwave clocks have reached their physical capacity. To measure smaller fractions of a second, physicists use visible light, which oscillates about 50,000 times faster than microwaves. Our ability to advance technology is currently limited by the physical difficulty of tracking these ultra-fast optical frequencies without introduced errors. If an atom moves even slightly during measurement, the Doppler effect ruins the frequency reading. The Doppler effect is a change in wave frequency that occurs when the source of the wave is moving relative to the observer. To eliminate this motion, physicists use intersecting laser fields to trap the atoms and hold them stationary. This trapping creates a complication called the A-Stark effect. The A-Stark effect is a phenomenon where the intense energy of a trapping laser physically alters the internal energy levels of an atom. This creates a paradox. The laser light required to hold the atom still enough to observe it simultaneously alters the frequency of time we are trying to measure. The optical lattice clock solves this problem using neutral atoms like strontium or ytterbium. Intersecting lasers create an egg carton lattice holding thousands of atoms to average their oscillations. A magic wavelength then shifts both upper and lower energy states identically. The trapping laser's interference cancels out, keeping the central clock transition unperturbed. Achieving this balance allows us to observe time without distorting it. To keep your feed balanced with more science, take a second to hit like and subscribe. However, packing tens of thousands of atoms into a tight optical lattice cause them to bump into one another. These collisions generate density shifts, which are errors in the clock's ticking rate caused by the interaction of nearby atoms. Two opposing forces are at play. Local interactions inside the same site pull the clock's frequency negative, while neighboring sites pull it positive. By tuning confinement to the magic lattice depth, JILA researchers forced these poles to perfectly equalize and neutralize. This breakthrough improved clock measurement precision by nearly 2 orders of magnitude. Optical clocks have reached an uncertainty level of less than 2 × 10 to the negative 18th. At this scale, the clock senses the warping of spacetime caused by Earth's gravity. In relativistic geodesy, the use of atomic clocks to measure the Earth's gravitational field, lifting an optical clock just 2 centimeters higher in elevation physically changes its ticking rate due to the weaker gravitational pull. The device functions as a gravitational sensor capable of mapping the physical fabric of the universe. The global scientific community is currently working toward a roadmap to officially redefine the SI second in the 2030s using these optical standards. Human timekeeping originated with the tracking of shadows cast across carved stone. Soon, our global standard for a second will be determined by webs of laser light holding quantum particles perfectly still. These devices provide the precision required to test the limits of general relativity and detect potential variations in the fine structure constant. We are just beginning to see what insights these sensors will provide.